Today we're describing the significance of particle interaction symmetry. So at atomic level, we have a particle colliding with another particle, right? Or interacting with another particle, I should say. So the question is, do we get the same reaction if we swap things around? To sum up this symmetry, there's three things you need to remember. This is the crux of today's lesson. A charge reversal symmetry is the first one. Write it down. So the way I'm hoping you will remember this is thinking about the formal coming up. If one girl gets a spray tan and nobody else does, is it awkward? A little bit. But if all of the girls get spray tans, is it good? Because then they're all like agreeing, right? So if we have all positive elements in the interaction, right? Positive at the start, positive, positive. If we swap everything to negative charge, it's good. Then it is okay. So they're all negative, but we can't just reverse one of the charges. Otherwise, we haven't done full charge reversal symmetry. All right, the next one is time reversal symmetry. Write that down. The analogy this time is if you break a glass or mug, like you drop it on the ground, right? You can't reverse that. But at an atomic level, you can do that. So this time it's the opposite to the analogy. You can reverse. So if you've got two things going in and two things going out, we can just swap them, right? So the two things going out, we could put them in and get the two things that were going in the first time. Basically the P and the E over here, we swap with the N and the V over here. So we could combine a neutron and an electron neutrino and create a proton electron. So this is the second type of symmetry. The third type of symmetry, I don't really have an analogy this time. We basically just move, you know, the arrow, it's like an equal sign in maths, yeah? You bring it over the arrow, and as we bring over the arrow to the other side, we need to do the antiparticle of whatever it was. So I've got some letters to show this. So if we got A plus B decays into C plus D, if we want to bring the B over to the other side of the arrow, we just have to have the antiparticle of the B. So just some further notes. I highly recommend you write this down. A photon is its own antiparticle. So what does that mean for the interactions? For example, the time reversal. Photon, bring it over there. We don't need to do anything with it. It's still a photon. My second point, we can move more than one particle. So you don't just have to do one particle, you can swap two particles. So like I said before, the symmetry shows us a reaction can occur, but the probability doesn't mean it necessarily will occur very much. The last thing, when we're thinking about this, conservation of energy and momentum must be obeyed. Also, baryon number, lepton number must be obeyed. There are other forms of symmetry as well. We're just looking at those three in this course. Symmetry works for most interactions, but not all. Symmetry is helpful because it allows new reactions to be predicted, like I just said. Violation of symmetry helps provide more information about the forces particles involved. So there might be another particle in the interaction because it's violating symmetry that we don't know about.